Were you there in the last class? You were there. You were there in the last class. Okay. If there is no inconsistency, then I will stop talking. I mean, it's okay. I mean, I don't mind. I have no problem if you're not attending or something. If I see very less attendance, I have absolutely no problem. I will just stop. There is absolutely no reason for it. Okay. If you think you can study on your own, then also I can stop. Okay. If you don't, I mean, of course, I will talk if you are attending. I absolutely don't have any problem with stuff. It will be easy for me. You directly prepare a question paper and give it to you. Okay. Okay. So today I want to, so before we want to start doing Fourier series, before that I want to well, I will not give a full proof in the full generality because we didn't talk about locally compact spaces. I will give a version of Stone-Weistrass theorem for locally compact spaces. So that's what we want to do in half of the class, hopefully. So, Ritabrata has given a tutorial. Did you attend? I think he's talked about locally compact space. Did you attend? Okay. So he has defined. So I will not give all the details. I think he has done. I don't know what he did. I didn't attend it. I mean, he told me what he's going to do, but I'm not sure what he exactly did. So I will, whatever is needed, I will just recall. Okay? So definition. X is, you can assume it's metric space, but topological space is fine. So it's said to be locally compact if for any x, for all x in x, there exists a neighborhood. So there exists, I mean, it just says that for any x, you have a compact neighborhood. So it says there exists a open ball around that whose closure is compact. So there exists, so you can state it in this way also. There exists a compact K with contains x, and interior of K is non-empty. It's also fine. There exists a compact neighborhood, which is with interior, non-empty interior. Or you can assume that there exists a open ball or neighborhood around that whose closure is compact. So for non-linear space, this is equivalent to saying open balls are compact. All open balls are compact. Yeah. Yeah, that's what I said, that there exists a compact, this is separately, compact K such that X is an element of K. Okay, X is in the, oh, okay. So maybe if you want that, okay. There exists a neighborhood, okay, let me just say that neighborhood, okay, maybe you are right, X in U with X such that U closure is compact. Okay, this is fine. Okay, this is fine. So you don't want it to be in the border. Okay, this is fine. So for a non-linear space, as I said, it's enough. I mean, this says that there is some open ball which is compact. Okay. So if all open balls are compact, then of course this is locally compact. I mean, that means the space is locally compact. In non-linear space, if some ball is compact, then you can shift it to get any other open ball. I mean, you can translate it, and the addition is continuous, so you can translate it to get another open ball, and you can enlarge it. You can dilate it. I mean, you can, if the radius is r, you can take it to any bigger r, and that will also, because multiplication is continuous, that's also compact. And compactness is a topological property. So if one ball is open, all balls are open in non-linear. Okay. So if one ball is compact, all balls are compact. Sorry, one ball is compact, all balls are compact in non-linear space. So so this is just a remark. We are not going to work with that. I told you the proof. Remark is in non-linear space, this is locally compact, is equivalent to saying there exists one open ball, which is compact, whose closure is compact. Okay. whose closure is compact. So this is equivalent to that. So when you have a locally compact space, you can compactify by adding one single element, and which is called compactification. So X is locally compact. This is just a symbol. Then you define X tilde to be X union, some one single element you add to that. You call that element infinity. Okay. So then you define a new topology on that. We have already defined what is topology. You don't need to work with. You can assume X is a metric space here. Okay. But this works for general topological space. You can define U contained in X tilde open if there are two cases. X is infinity is in U, then U complement is compact. This is contained in X. If infinity is not in U, then U contained in X is open. I mean, you have your original metric space X, and you define a new set X tilde by adding one element, and you have to define the topology on this X tilde. You have to define the open set. So if a set is contained in U, if it is open, if it is earlier open in the earlier topology. If it contains infinity, it is open if and only if its complement is compact. Okay. I think he did all that. Okay. So this is, so now you can this is some, this is exercise. Okay. I will tell you orally, but since he has done, one thing is, this is, okay. Let me say this, tau tilde. So tau locally compact and tau the collection of open sets. Okay. This is the topology on the collection of open sets. Then tau tilde equal to U contained in X tilde. If infinity is in U, U contained in that, such that if infinity is in U, then U complement is compact. If infinity is not in U, then U contained in X is open. So this is tau tilde. Then the exercise is tau tilde is a topology on X tilde. Very, you have to consider several cases, and the verification is easy. So you have to go clearly X tilde is open. Of course, X tilde is complement is empty set is there, original one. And similarly, empty set is already there in the X. So so the empty set and the whole set is there. And you have, so if you take two, if you take intersection of two U1 intersection U2, then you have to consider two cases, infinity is there or not. Then, similarly, it will be clear. Okay. So you can work it out. This is one statement. Second statement is X contained in X tilde is open. That is clear because X is originally open. That's the whole set in the original topology tau. Then the third one is X tilde is compact. This is also easy to verify. So if we have open cover for X tilde, it's a cover. So one of the the cover has to contain infinity. So that set's complement will be compact, and that has to be covered by the remaining sets. Okay, that will have a finite subcover, and that finite subcover together with this set will cover X tilde. Yes. You assume X is metric space. We are working with metric space. That is not complicated. You will learn these things in the topology course, next course, because you will not see the Stone-Weistrass theorem for that. So that is why I am doing it. Okay. So we are worried about only metric space, and we are worried about only real line, Rn, those kind of non-linear space, those kind of. We are worried about non-linear space. We are not even worried about other spaces. Okay? And in fact, so this X delta is compact is clear. I think he did, Ritaprada did this in tutorial. If you have attended, you would know that. So X delta is compact because if there is a open cover for this, one of them has to contain infinity. The remaining thing should cover the U complement. I mean, if U is one cell which contains infinity. Okay, this is an exercise. You will do that. I'm just orally telling you the proof. So that because that covers a compact set, that has to have a finite subcover, and that with this set will cover the X delta. Okay, so you just think about it, it will be clear. So X delta is compact. So what is there is nothing else I need, I think. Okay. So using this, I want to prove the following theorem, Stone-Weistrass. I mean, we have several things to introduce, several notations and notions to introduce, but let me just state it. So, okay, before that, let us notice something. The definition. F is a continuous function. F is in C of X. X is locally compact. Then we say F vanishes at infinity. This is just a definition. There may not be any infinity in X. Okay? Vanishes at infinity. If given epsilon greater than 0, there exists a compact K which depends on epsilon contained in X, such that mod f of X, I mean, f is a real valued or complex valued function. Okay. So whenever I say like this, it's a real valued or complex valued. Mod f of X is less than epsilon for all X in K. K epsilon complex. So given any epsilon, there will exist a compact set which depends on the epsilon. Outside that set, the value is modulus of that f of X is less than epsilon. The function is less than epsilon. This is what is called vanishes at infinity. This is the definition of vanishes. So X is locally compact, then C0X equal to all those F in C of X. And F vanishes at infinity. So, I mean, exercise, maybe assignment, maybe C0X is a Banach space, is complete. I mean, that is what it means. Complete non-linear space. That is what it called as Banach space. So, I mean, with respect to what? With respect to norm F infinity. So for that, you have to first verify that this is finite. So if F is in C0X, it is bounded, you have to verify. That is clear, right? I mean, given an epsilon, you can find a compact set. Outside that, it is less than epsilon. On the compact set, it is bounded. Continuous functions are bounded. So it is bounded. So the supremum exists, number one. So then you have to prove that this is complete. To prove complete, you have to only prove this is closed inside all bounded functions. We have already proved we have any set, bounded functions on that set forms its non-linear space. We have proved. So you have to only see, I mean, but on the other hand, if it converges in this norm, that means it converges uniformly. So uniform limit of continuous function is continuous. So that is done. All you have to verify is vanishing at infinity. That's all, which you can, I'm sure you can do it. Okay. So that is the exercise. So this is a complete non-linear space. Notice that it's also an algebra. You can multiply two functions. That will again be in that. You can multiply pointwise. That will be again in that. Okay. And you can add. All these things you can verify. So it's a norm. It's a complete algebra. Okay. So let me state the theorem now. I think that is enough. I think that A contained in C of X. X is locally compact here. Is is a subalgebra. By subalgebra, I mean if you have F and G in A, then the product is also there. That is enough for the subalgebra. And it's also a vector space. Algebra, I mean, is a subspace. I mean, subalgebra means is a subspace which is closed under multiplication. Okay. So this is a subalgebra which separates points, of X. Okay. And there should be one more condition, and does not vanish. I will write what it means. It does not vanish on X. That is, there does not exist any X naught in X such that f of X naught equal to 0 for all F in A. Okay. That means that is equivalent to saying for all X in X, there exists a F in A such that f of X is not equal to 0. Okay. So given any X, there exists something which, I mean, okay. This is equivalent to saying the function vanishes at infinity. If you add a point, it will vanish there. We are going to see. Okay. So it separates infinity and any other point. That's what it means. I mean, just to give you the idea. That's what we are going to use. And then we use the earlier Stone-Weistrass theorem. Then A is dense. That's all, no? A is dense in CRX. So this is what we want to see. You have a locally compact metric space. Let us assume it's metric space. Incidentally, I don't know whether you attended that the brother's thing. Did he prove that something is a locally compact space? The completion is metrizable, not the completion. The one-point compactification is metrizable if and only if it is separable. So, okay, so he has done that. So, if you have separable, if X is separable, then the X delta is metrizable. Okay. So you can assume that this is metric space and X delta is metric space. The one-point compactification is also metric space. So we want to prove this. Okay, this is the theorem we want to prove. A is dense in CR. Say it again. C naught, sorry. Yeah, C. Huh? Yeah, sure. So it is real value for the time being. So the same theorem will work for complex valued if you have to name. The same theorem for complex valued function will work for complex valued. Yeah, we have to take real value function here. Yeah, this is C0, and then it should be real value for this statement. Otherwise, you need the conjugation to be there. Okay? And that I will not state, it's clear. The same proof will work. Okay. So to prove this, we prove the following. So let's recall the Stone-Weistrass theorem. I will state it in a slightly different way. So X is compact for the time being for this theorem, and A contained in C of X, let's say R. Okay. It separates points of X and does not vanish. I mean, does not vanish or vanishes nowhere. Vanishes nowhere. The same definition. Nowhere in X. Okay. This is equivalent to saying it contains constant. No, it is equivalent to that. We'll see that. Okay. No, vanishes nowhere in X. Then A is dense. Okay. So all we have to prove that we need to prove vanishes nowhere is equivalent to saying contains constants, right? A vanishes nowhere It's equivalent to saying A contains constants. Okay, that's what we have to prove. I mean, then the original Stone-Weistrass theorem will imply. So, okay. So if it contains constant, then it does not vanish because constant functions does not vanish. So this way is clear. Okay. So we have to prove only this way. So if it vanishes nowhere, we have to say it contains constant. First, we claim the following. Claim there exists a F in A, maybe a closure, because we're going to take maximum. A closure. Okay. I mean, if you just think about it, in the original Stone-Weistrass theorem, it is enough if you assume A closure contains constant. Same proof will work. It is not A should contain constant. Okay. So A closure contains constant is fine. Okay. The same proof will work. There is really no difference. Okay. So there exists a F in A closure such that F does not, single function does not vanish. This is my first claim. Such that F of X not equal to 0 for all X in. This is the same as the proof. I mean, this is very similar to the proof of proof we have done. So first, it does not. I mean, we are assuming that it does vanishes nowhere. Then we want to prove. Then we want to prove this claim. I mean, we want to prove. We assume it vanishes nowhere. Then we want to prove that it contains constant. First, we are proving this claim. Okay? So there exists a function such that F of X not equal to 0. So for X in X, for any X, for any arbitrary X, okay, we are. I mean, for this function, we are fixing this X, but it's arbitrary. For any X in X, there exists a function F of X such that F of X in A such that F of X at X is not equal to 0. Okay. You can assume the function is positive, it's real valued. You can take the square and you can assume it's positive. Do I need that? Yeah, you can assume it's positive. So without loss of generality, assume by multiplying by some number, assume that F of X is equal to 1. Now this proof is very similar to what you have done. Then you define Ux equal to all those y in X such that Fxy is greater than 1 minus X. This is open and X is in Ux. Okay, so X is equal to union of Ux. Okay, the same proof. I mean, same idea. So there exists Ux1 up to Uxn such that X is equal to union of Uxi is equal to 1 to. Okay. Now define F is equal to maximum of. We know that this is in the, we have earlier seen that this is in the closure. F is Fx1, Fx, yeah. Okay. And F is in A closure. As I mean, which we have already proved. I mean, if it separates points, then we have proved that the maximum and minimum are there. Yeah, we use only separate points, no? Yeah. So okay, now we know that since it is maximum, F of X is greater than 1 minus epsilon, so which is not equal to 0, of course. That is our claim. The claim is proved. Okay. Now we want to get a function. I mean, we want to get constants. Maybe it is easier. I may be complicating, but this is one way of doing it. So now we have a function which is strictly positive. I mean, okay, it's not just, it's not equal to 0. F of x is strictly greater than 0. I mean, I changed the claim. That is what we have got. We got a function which is strictly greater than 0. Since it is a compact set, there will be a minimum which is positive, right? So f in C of x, and f is strictly greater than 0 on x. Okay? So there exists a m such that f of x is greater than m for all x, and m is greater than 0 for all x in x. Without, okay. Now you defined g on this 0 norm f on this interval by, you can just take the line g of 0 equal to 0 and g restricted to m norm f infinity equal to sm1 or any constant. You can take the line joining 0, 0 and 1m, sorry, m1, and then extend it by constant up to norm f. Okay. By original Weierstrass theorem, there exist polynomials Pn, I mean, which are polynomials in 0 norm f, okay, such that Pn converges to G uniform. Since G of 0 equal to 0, you can assume, I mean, you can subtract Pn 0 if you want. Pn minus P of 0 will converge to G minus G of 0, which is G. So we can assume Pn of 0 equal to 0. That is, it does not have any constant term. Any doubt? Any problem? No problem. Okay. So this polynomial does not have any constant terms. Okay. So because it does not have a constant term, Pn of f, if you apply Pn to this f, okay, our original f, that is in A closure. A closure is an algebra. Okay. A is an algebra, A closure is an algebra because multiplication is continuous, all that. So Pn of f is in A closure. I mean, Pn of f does not contain constant term. If it has constant term, then for that to be in A closure, constants has to be there. Of course, that is what we are trying to prove. Okay. But then Pn does not have any constant term. It will be just powers and sum of powers of f. Okay. Because it's an algebra, they will all belong to that. So Pn of f is in A closure. Okay. And Pn of f converges to, but then Pn of f has range between m to norm f. Here this g is 1. This will converge to g of f, which is identically uniform. So constants are there, are contained in A closure. That's all. So we have proved that this version of Stone-Weistrass theorem. This is the proof in Rudin, but that is the standard proof. Right. So we can show that, I mean, instead of going through all the details, we can do that. What is that? I'm saying that Pn of f will converge to G of f. G of f, if the range of f is between m to norm f. There G is 1. So because of that, G of f should be 1. We have defined it like that. You can take any constant, then any constant will be there. So 1 is there, all constants are there. Fine, that's all. So we have proved that theorem. If it vanishes nowhere and it separates points, then it is dense. Okay. Okay. I have defined what is called an isometry for metric space. The same idea will work. For normed linear space, isometry means it has to preserve the norm. Okay. So, I mean, it is just you can identify this with that. So this is the proposition. It's direct. C0 X, X is locally compact. Compact. It's isomorphic to all those F in C of X tilde such that F of infinity equal to 0. This isomorphism, that is what this symbol, what it means is there exists a T from C0X to this one, F in C of X tilde. Functions vanishing at infinity. This is vanishing at infinity means really vanishing at infinity. This is by definition vanishing at infinity, whatever. Okay. Such that T is linear, bijection, and it's a homomorphism. That's what we mean by an isomorphism. A bijective homomorphism means ring homomorphism. It will take product to product. And it's linear. Linear means linear, vector space linear. And it's continuous also, but instead of continuity, you can say that this T of F, norm of T of F in X tilde, in C of X tilde, is same as norm of F in C0X. When you have that, it preserves all the structure. You can treat those two as same space. If we have two sets, just set, if there is a bijection between them, you can treat them as same set. There is no difference. But if you have a vector space, then if there is a isomorphism between them, linear isomorphism between them, it's more or less like it's like a same vector space. So if you have a normed linear space where you have a norm, okay, and if you have a linear bijection, and it also preserves the product, okay, an algebraic homomorphism between them, and it also preserves the norm, then it will preserve the metric also. So they are like essentially same objects. Okay. So whatever you want to prove here, you can prove for this. Okay. Now the proof follows immediately, whatever you want. So now if you have any A here, script A here, algebra containing here, then you can take this algebra here and you can prove it here and bring it back there. Okay. This is not part of the syllabus. I am just stating it. Okay. There is no syllabus, there is no local compactness. So now the theorem, Stone-Weistrass theorem, I have erased it. Okay, just erased it. Locally compact and A contained in C0X, okay, and which as is real, which separates points, vanishes nowhere, separates points and vanishes nowhere. Okay, then A is dense. Okay. So the proof is clear now. Should I repeat it? Same proof, right? You have to prove that. So you have a here. You can bring it here. This is compact C of X. Okay. There it separates points and it does not. And it. Oh, I forgot. Sorry. It is not clear. I have to prove. I didn't prove. You should say that it's not clear, no? When it is not clear. Okay. So it is not clear. If I prove the following theorem, it will be clear. Which is also Stone-Weistrass theorem. Okay. This version. If I prove this version, then it will be clear. Okay. I didn't prove it. My intention was to prove that there, but I didn't do that. So that A contained in C of X, X is compact. Maybe you are also not listening. You didn't find that mistake. Okay. So A is in C of X. Okay. X is compact. Okay. A separates points. Okay. Then either a closure equal to C of X. I mean, I'm saying C of R. Okay. For C of complex valued function, you have to take F bar. The same thing will work. Okay. So either A is equal to either A closure is C of X R, or there exists a X naught in X such that A closure equal to all those F in X such that F of X naught equal to 0. So this is the statement. Here one condition is missing. It separates points we are assuming. We are not assuming that it vanishes nowhere. If it vanishes nowhere, then it will be equal to this. So if it does not vanishes nowhere, then it has to vanish at some point. That's what it means. Okay. I mean, it cannot vanish more than one point. Then it will not be separating point. Okay. So it has to vanish at one point. Then it has to be equal to this. Okay. So you have to prove that this is equal to that. So we will prove this. Proof. So suppose, should I write it? I mean, it's clear. Suppose if A does not vanish on X, of course, then A closure equal to C of X. Okay. Otherwise, there exists X naught in X such that F of X naught equal to 0 for all F in A. Right? And we want to prove that. We want to prove this statement. Okay? A closure is this. Okay? Now consider A tilde equal to all those F from C times 1. I mean, C means it is constant function. Okay, this is clear. No? C F plus C times 1 means it's constant function. You are adding constant function. F in A and C in R. Okay. Okay. Now this contains constant, and the A separates points means A tilde also separates points. Okay. Now A tilde contained in C of X separates points and contain constant. This is just vector space direction. Okay. Constant functions is a vector space, one-dimensional vector space. So we're just taking the direct sum. You must assume direct sum in vector space. It is just direct sum of that. So it's a vector space. I mean, you have to verify all that actually. So it's a vector space. It's just direct. You can verify that it is that vector space. You can add and square multiply. It's a vector space. And you have to verify that it's an algebra also. If you multiply two things, F plus C1, F2, F1 plus C1, F2 plus C2, then the multiplication will be F1, F2, which is because A is an algebra that is in A. And C times F1 is again, because it's a vector space that is in A. And similarly, and C1, C2, it's a constant. So you have to verify it's an algebra. Okay. Then A is an algebra. And it separates points because original A was separating points. And it contains constant because we have added the constant. So this implies A tilde closure is equal to C of X. Okay. In particular, if F is in A closure, I mean, or if we have any, that's not A closure. So suppose what we have to prove is A closure is equal to this. We have to take any function which satisfies this condition, and then we have to approximate it some by functions in A. Okay. So suppose F of X naught equal to 0 for some F is in C of X. Okay. Then we want to, but then A tilde closure is whole of that. So there exists Fn plus Cn times 1, which converts to F, right? By the original statement. Okay. Okay. Now Fn, I mean, at 0, it has to converge to at 0, the, I mean, this uniform convergence. This is uniform convergence, of course. So at 0, it has to converge. So Fn 0, of course, at 0, it is Cn will converge to F of 0. Oh, sorry, at x0, it has to converge, not 0. x0, it has to converge. Okay. This is equal to 0, and this is equal to 0, of course. So this implies Cn goes to 0. Right? So this implies now you take Fn minus F, norm of F infinity, which is less than or equal to Fn plus Cn 1 minus F plus norm Cn. Norm Cn is just mod Cn. So this goes to 0 by the original assumption. Okay. So we have proved that A closure is equal to all those F such that F of x naught equal to 0. Clear? Elementary proof. Okay, now from this, that theorem follows. Right? Should I write the details? This says that if you have something inside, if the X is locally compact, this is an algebra contained in C0X, then by this isomorphism, you can take that algebra into C of X tilde, okay, where with F of infinity equal to 0, because it vanishes nowhere, but it vanishes at infinity. Infinity and any other point can be separated, and it, I mean, then you can use this version to prove that this, I mean, that image or whatever the image you have taken inside that, I leave it as an exercise. Okay, this theorem is exercise. Or should I give it an assignment? So assignment. Okay, this is assignment. Okay. So you write the identification, whatever I have written. It's all very simple thing. Okay, then you use this theorem. You don't have to prove this theorem again. You state this theorem so that you understand the whole thing. So then you prove that. Okay? It's very direct. Okay, so that's all for Stone-Weistrass theorem. Okay, you want to start some new topic. If you want to write, you write it, and then I will erase and start a new topic. Assignment, okay? If you have done some linear algebra and you know what is inner product space. We anyway defined it in the first class. Okay. So once you have inner product, you can talk about, I mean, inner product is like, I mean, if you have a vector space, which is linear, you can talk about lines. Okay. And then normed linear space is something like modulus. You have a magnitude or something for an element. But if you have two elements, you can talk about the angle if you have an inner product. That's what inner product is about. I mean, more or less, it's a generalization of angle. Okay. So you can talk about angle being 90 degree. Okay. That's what is called orthogonality. So if inner product between two element is 0, then it's what is called orthogonality. And you cannot have too many orthogonal elements in a vector space, right? In an n-dimensional vector space, you know that there are n, exactly n maximum number of orthogonal elements is n of them. And you can write, so that forms a basis also. Or if you have an maximal orthonormal set, then that forms a basis. So you expand any element using that basis. This we want to develop. This can be developed to infinite dimension or any function space also. Okay. So so if you have any, so let's define one. So let's make the definition first. Definition. So I use this letter H for the vector space now. Okay, this is a vector space. This is an inner product space. H with an inner product is an inner product. Okay. So if you have an inner product space, then you can define norm X equal to X, inner product is X, which is positive. One of the assumptions, inner product means it is linear in this variable. Until if you are a physicist, it's the other way. Okay, it's linear in this variable, antilinear, it's conjugate linear. You can take a complex. This is over vector space over C. Okay, vector space over inner product space over C. We are working with C. Okay, so and this is linear in this variable, conjugate linear in this variable, and this is greater than or equal to 0. This is positive definite, and this is equal to 0 if and only if X is 0. Okay, so these are all the yeah, I'm going to write now X. This is equal to this. I didn't finish. Yeah, this is positive, so you can take the square root. Okay, so this is the norm. So you get a norm. So once you have a norm, you have a metric on that. So it's a metric space. Okay, so this is a Hilbert space. H is a Hilbert space. This is just a word. Okay, this is a Hilbert space. We are not going to study Hilbert space or something. This is just a definition. If H is complete with respect to this norm, okay, every Cauchy sequence converges in this norm, then it is complete. Okay, then it is a Hilbert space. Okay, okay. Now in this, and you know that any metric space can be completed. That also we have seen. Okay, I think 2 proofs are given to you. Okay, so example, of course, the one example is L2, all those xn sequences such that summation mod xn square is finite. Okay, n equal to infinity, n equal. This is an example of a Hilbert space with inner product between xn. It will follow by whatever we call as Cauchy-Schwarz. This will be summation xn yn, area bar. Okay. This is the inner product, and this will be a complete. We have seen that it's complete. Okay, we have seen a proof that it's complete. Okay, so this is an example of an inner product space. Or we can do something. We define an inner product space and then complete it. This is because we haven't done measure theory. I'm using this definition. Okay, so you take C of X, that H is equal to H. Take C of X. You take C of X with uniform. We have uniform norm. With respect to this, it is complete. It is not complete with respect to some other norm. We have seen that, I think. Okay, so define norm F2 for F in C of X. C of let's say take an interval, is enough. Okay? 0, 2 pi or whatever, AB, whatever, AB. Okay? You take a continuous function on the interval AB, then you define norm F2 equal to, or inner product of F and G2 equal to integral over A to B F G bar. Okay? With the usual Riemann integral. Continuous functions are Riemann integrable, so it's fine. Okay? So Fg with respect to F of T, G of E bar dt. Okay? This is well defined. It's integrable. Continuous functions are integrable in this, and it's well. So this is the inner product. You can linear, antilinear, and if you have mod f, if you take ff, it will be mod f square, which is greater than 0. And the continuous, I think we verified that also. If it is integral mod f square equal to 0, then f is 0 for continuous function. Okay, so not in general, but for continuous function, that is true. We verified this now. Integral mod f square is 0 for continuous function, then f is 0, identically equal to 0. We proved it. Okay? So this is a genuine inner product. So this gives a norm on that. Okay. Now you define L2 of this AB, capital L2. There I have written small L2 is equal to C of X completion with respect to, so norm 2 equal to this integral mod F square. Okay. Norm F2 is this. This is with respect to norm 2. I mean, it's not closure, it's completion with respect to norm F, norm 2. We have a norm on C of X. You complete it with respect to this. Okay. This we call it as L2AB. This can be directly defined using measure theory, but I don't know, some of you attending measure theory course, then when graduate analysis 1, they maybe not now. But in my course, some second year students used to attend. So I don't know whether any of you are attending. So this is one way of defining L2AB. And this is complete because you have taken the completion. And C of X is not complete with respect to this. Okay. We have seen this. You can have just if you, something may not converge in uniform. If it converges in uniform, it will converge in this norm. Okay, but something converging in this norm need not converge uniformly. Okay, I think we have seen that. Okay, so this is another. This is what we are going to deal with. Okay? We are going to deal with this inner product space. Okay, so the definition is clear. You take continuous function. We will be dealing with continuous functions only, but we have to deal with inner product space. So I am completing it with respect to this inner product. Okay, that's all. Okay, so this is a general definition, okay, which is an Hilbert space, which is a complete inner product space. Okay. Then as a set. Okay, let's say this xy in H and X said to be orthogonal. Denoted by X is orthogonal to Y if the inner product between them is 0. That's a long definition, but this is the. Okay. If the inner product between two elements is 0, then we say they are orthogonal. So I want to make some statements about orthogonality and stop this class. So another again definition. A set, say some S contained in H, okay, is said to be orthonormal. The set is orthonormal. Okay. If E is in S, then norm E equal to 1, and norm with respect to the inner product. And if you have E, F, two element in S, then and E is not equal to F, then the inner product between them is 0. If you take any two elements, they are orthogonal, and their norm is 1. Ortho means orthogonal, and normal is norm is 1. Orthonormal. Okay. Then the proposition. H is separable, then any orthonormal set is countable. Okay. I'll make more statements later. Proof. So we assume H is separable, so it has a countable dense subset. Okay, that Xn contained in H is countable dense subset. Countable is there already. Then subset. Come on, this is a some dense subset. We want to prove S is countable. Okay, so let it be there. So E and F are in S. Okay, then and E not equal to F. Okay, then the distance between, let us calculate the distance between E and F. So whenever we are in inner product space, usually you will not be able to compute the norm. I mean, there is no way to compute the norm. But what I mean is, as it is norm, but you have to compute the square. Okay, that's how you relate to the inner product. Okay? So you E F square, which is equal to E minus F, E minus F. Okay? Then we use the linearity. E is 1. The inner product in E is 1. F is again 1. All other inner product is 0. So this is equal to 2. So this implies the distance between E and F is root 2. Okay. So if we have any open ball with half the distance or maybe 1/4 of the distance of this, then it cannot contain two elements of this. Okay. So this implies B of any open ball Xn with root 2, maybe you divide it by 4, 3 if you want, okay, then can contain at most 1. At most 1 element from S. Okay. So it's countable. This is B of Xn. This is indexed by. So this implies S is total. Okay. So let's make more statement. Any orthonormal set is linearly independent. So proof. So you have to take some n number of, I mean, finite linear combination. You have to say that all C and the constant has to be 0. Okay. Let's suppose that summation Cn En equal to 0. Okay. Cn, okay, n equal to 1 to n or something equal to 0 for some En orthonormal. Okay. Then you have to prove that these Cn's are 0. Finite linear combination, if it is 0, then Cn has to be 0. That's what we want to prove. And you just take inner product with some Ei, call it X, then X Ei. If you take the inner product is here you get summation Cn En. You can take the summation out because its inner product is linear, and Cn also out. You will get En Ei, and except for n equal to I, it's all 0. So this is equal to Cn. This is equal to 0, and the inner product between 0 and n element is 0. So this is equal to 0. So Cn equal to 0. That's what you want to. So they are linearly independent. Okay. Next proposition. So I mean, it's a countable, I mean, orthonormal. So let's assume, I mean, from here onwards, we know that this is C of X is separable. Did you prove it? Huh? I don't remember. Anyway, I'll check it. C of X is separable means there exists a countable dense set in the, well, if we prove C of X is separable, you'll prove it again if I am true. Okay. If C of X is separable, so there exists a countable dense set in the uniform norm in C of X. But uniform convergence will imply you can take the convergence inside the integral. Okay. So the L2 convergence will be guaranteed if you have if there is uniform convergence. Okay. So that countable set is uniformly, if uniformly dense means it's dense in this L2 norm also. So it will be dense in the bigger completion also. Okay. C of X closure is that in that. So this dense set, if you close it, so we will go through it again. So in particular, that our L2 is separable. Okay. So we are going to deal with that. So our Hilbert spaces are separable Hilbert spaces. Okay. So our orthonormal sets are countable. Okay. That's what I wanted. So suppose, so we want to work, so we will work with countable orthonormal sets. Let E1 up to En finite set be orthonormal. And first statement. Summation Ci, Ei. I mean, that is trivial anyway. No, what I wanted to state is trivial. It will be part of the proof. What I want to say is the following: 1, X is in H. Okay? Then summation Ci X Ei. Okay? I equal to 1 to N. You take this. This is a no Ci. Sorry, this is a Ci. This is a number. So this is Ci. It's a linear combination of this Ei. Eis are vectors. This Ci Ei is a number, complex number. This is a vector. You are adding this vector. So this is a vector in X. Okay. Now I take X minus this. Okay. So this is a vector. This vector is orthogonal to Ei for all. Maybe here I have Ei for all j. Okay. This is the statement. Okay. So second statement is, this is what is called Bessel's inequality. Which says that we have fixed that is orthonormal. Okay. Summation X Ei mod square is less than or equal to norm X square. I mean, this will be true for infinite one also. Okay, we'll state it as the next statement. This for finite one, let us state it and then. Yeah. So proof is direct. First one. So you want to prove that X is Ej is orthogonal to this. Okay. I want to take the inner product with this. First element, you get Xej. Second thing, you have E1 up to En. It will pick only Ej. You will get Xej, which is 0, right? You want to consider this. You call this Y. Okay. Then Y Ej equal to Xej minus summation Xei Ei Ej. And that will only pick Xej, right? Minus Xej equals 0. Right? X minus this term. You want to take the inner product with Ej and show that it is 0. If you take inner product with Xej, here you have linear combination of Eis. Ei Ej is 0 and I not equal to j, only Ej will be picked. So that's what you get and it's 0. So Ej is orthogonal to this. So this is some element which is orthogonal to this. Okay, so you have to note this. Note if x is orthogonal to y, and this is Pythagoras theorem, okay, then norm x plus y square is equal to norm x square plus norm y square, right? This is equal to x plus y, x plus y. Okay, this is equal to x plus y, x plus y. X square, x, if you take inner product, x square, y square you get, and then other terms will 0. Okay, so this is equal to that, right? So if x is orthogonal to y, this is true. And this is true for by induction. I mean, if x and y1 are x1, x2, x3, they are all mutually orthogonal. x1 plus x2 is orthogonal to x3. So by induction, okay, you have the orthonormal set. So E1 plus up to or any orthogonal elements. Any if x1 up to xn are orthogonal, then the summation norm square is individual summation square. So individual summation norm square. Norm of the summation norm square of the summation is summation of the norm square. So by induction, summation xi square equal to summation norm xi square if x1 up to xn are orthogonal. Okay. So now we have proved that x minus summation xei ei, this is orthogonal to ej. Okay, right? So this implies x, this call this as y. Now y plus summation xei ei is equal to x, of course, right? I'm just subtracted this and then adding this. So this is equal to x again. So the norm should be equal both sides. So norm x square equal to norm y square. I mean, they are all orthogonal. Y is orthogonal to this. They are all orthogonal. So this square equal to this norm square, which is equal to norm square plus norm square of this. But they are all mutually orthogonal. Okay. So mod of norm ei square you will get. I mean, if you take the norm of this is scalar, that will come out as square, and this has norm 1. We have assumed it has norm 1. So because of that, this is true. So norm x square is equal to some positive element plus this. Okay. So this implies summation norm x ei square mod square I equal to 1 to n is less than or equal to norm x. Sorry, you are not able to see. Norm x square. Shall I read it? Eh? What's it? Bag. Oh, this bag. Oh my God. Sorry. Fine. Okay, computer also. Okay. My handwriting is not a problem. Okay, I thought handwriting. It's okay. It's direct. There is nothing. We have used the fact that this is orthogonal to this, and you take the sum of this and sum of individual square, then square equal. From that we got, which is what is called Bessel's inequality. Now this is, there is nothing about finiteness. We can take any countable orthonormal set. So let us do the proposition. S is H is, of course, we assume H is a separable Hilbert space. Okay, it is always separable inner product space, which is complete Hilbert space, and S is an orthonormal set. Normal set in H. Then, of course, countable. Okay? Countable. Or you can take even up to En. So let's take even up. En, n equal to 1 to infinity. Okay? I want it to be infinite. Okay? So it's infinite dimension contained in H, orthonormal. I mean, it may be finite also if it is finite dimensional. I mean, it cannot be infinite, but we are assuming that it has a countable orthonormal. Okay. Then summation n equal to 1 to infinity mod of x en. These are all numbers, right? Complex numbers, and you have taken modulo square is less than infinity. Okay. As a consequence, I will write the consequence later. Proof. You use that theorem. That says that summation mod x ei en square n equal to 1 to n is less than norm x square for all n. So n going to infinity implies summation n equal to 1 to infinity x en square is less than or equal to norm x square. So it's fine. So this is absolutely convergent series. You take any element x. This is for all x in it. You take any element in H, you take the inner product, and you have an orthonormal side. You take the inner product xen, take the mod square, okay, and then it's absolutely convergent. Okay, that is the statement. So this gives the following corollary: x is in H, okay, then xen goes to, and en is, en orthonormal set in H. Okay? Then xen goes to 0 as n tends to infinity. Corollary is clear. Of course, this series converges, so it has to go to 0. Okay. This is what is called Riemann-Lebesgue lemma in Fourier series. You'll see that. It will follow, I mean, abstractly it follows immediately by a nice way. This is what is called, in Fourier series, it's what is called Riemann-Lebesgue lemma. We will prove it, we will write all the definition, then it will follow immediately. Okay, this is what is called Riemann-Lebesgue lemma. Okay. We'll see this in the next class.